right, so in today's lecture, we're going to talk about some properties of binary operations, the first two of which are associativity and commutativity. So let's start with a binary operation on a set S here. We'll call it star. And the operation star is commutative if S star T equals T star S for every pair of elements S and T in the set. So commutativity just means that you can reverse the order of the operation and it doesn't change the value. And then associativity is when you want to star three elements. Now, we don't want to change the order in which we star them, but you can only star two things at a time. So if you want to do R star S star T, then you could choose to do R and S first and then get a result and then star that with T. Or you could do S and T first, star those, and then star the result of that with R, as long as you're keeping the order in the same way. If associativity means it doesn't make a difference which way you do it, like which two you choose to do first. So for example, let's consider addition and multiplication on the integers, or the rational numbers, or the real numbers. It doesn't really make a difference. Addition is commutative. This is just a property, an axiom of the integers actually, for every a and b in the integers, or the rational numbers, or the reals, a plus b equals b plus a. Multiplication is also commutative for every a and b in the integers, or the rationals, or the reals. A times b is equal to b times a. Addition is also associative. A plus and then grouping b plus c together is the same as doing a plus b and then adding that to c. Same thing for multiplication. A times bc is the same as ab times c. But not every operation is commutative or associative. For example, let's look at subtraction on the integers or the rationals or the reals. So subtraction is not commutative. I think we all know. You can't reverse the order of subtraction, right, and get the same result. For example, as a counterexample, 1 minus 2 does not equal 2 minus 1. And subtraction is also not associative. For example, if you do 1 minus 2 minus 3, that's not the same result as if you do 1 minus 2 and then do minus 3, because on the left hand side you get 2 and on the right hand side you get negative 4. How about division? Well, again, I think we know that division is not a commutative operation because it makes a difference which way you divide, right? So here we're doing this on the reals minus 0 so that we avoid dividing by 0. Yeah, but if you do 8 divided by 4, that's not the same as 4 divided by 8, because on the left-hand side you get 2, and on the right-hand side you get 1/2. Division is also not associative. So if you do 1 divided by 2 divided by 3, that's not the same as if you do 1 divided by 2, divide that by 3, because on the left-hand side you get 3/2. So 1 divided by 2/3 is 3/2. But on the right-hand side, you get 1/6. 1/2 divided by 3 is 1/6. Another example, composition on Sn. Remember, Sn is the set of functions from the set 1, 2 up to n to itself that are bijective. And remember, we had like the 2-row notation and the cycle notation for these types of functions. But anyway, we know that composition is a binary operation on this set. And we do know that composition is associative. We had a theorem that said in general, composition of functions is an associative operation. So we know f composed with g composed with h is the same as f composed with g composed with h, like that. And that's true for every f, g, and h in Sn. On the other hand, composition is not commutative. I mean, for example, if I had f was the permutation 1, 2, 3, let's say in S3, and g is the permutation, I don't know, let's say 1, 2, then if you do fg, that composition, then let's see what that work out to be. 1 goes to 2 and g, and then 2 goes to 3, so you get 1 goes to 3, and then 3 goes to 3, 3 goes to 1, and then 2 probably go to 2, 2 goes to 1, yeah. So fg is 1, 3, and if we do it the other way, gf, 1 goes to 2, 2 goes to 1, so 1 is fixed, 2 goes to 3, 3 goes to 3, so 2 goes to 3, 3 goes to 1, 1 goes to 2. Yeah, so that wraps off like that. And certainly these maps are not equal because, for example, the first composition, FG sends 3 to 1, but the GF sends 3 to 2. So FG certainly does not equal GF. One more sort of basic example. We'll look at union, intersection, and set difference on the power set of S. So we know from a previous theorem that these are binary operations on the power set. Now we know union and intersection are commutative and associative. These are just basic set properties that, in fact, we had a list of basic set properties in the form of some proposition or theorem back in the chapter on sets. And in that proposition, we saw that A intersect B equals B intersect A union B equals B union A. So there's the commutativity property. And we also had the associativity property for union and intersection there as well. Set difference is neither commutative nor associative. Making that argument will be a problem that we'll work out when we do a skills check in a moment. Okay, here's an example that we saw on a homework to verify that it was a binary operation. This one, A star B equals A to the B on the natural numbers. So is it commutative? Is it associative is the question. Well, I don't believe it's commutative because, for example, if I do 1 star 2, 1 and 2 are both elements of the natural numbers. That would be 1 to the 2, which is 1. While if I do 2 star 1, I get 2 to the 1, which is 2. And so those two things are not equal. And for B, I don't know if we could do something like 2 star 1 star 3. And let's say we group it this way. Well, that would be 2 to the 1 star 3, which would be 2 to the third. So this would come out 2 to the third equals 8. While if we do 2 star 1 star 3, that would be 2 starred with, okay, 1 star 3 is 1 to the third power. So that's just really 2 star 1, and 2 star 1 would be 2 to the 1, which is 2. And so here we see that the associativity property does not hold, so it's not associative. All right, so let's do a little skills check here, just to see that you got the idea of how the commutativity and associativity property work. So in part 1, I'm defining some binary operations that they're not just usual binary operations, but they're these sort of contrived operations. The first one is defined on the integers by A star B equals A plus B plus AB. And then the second one's defined on the reals, and X star Y would be XY plus 2X on this one. So I want to check, is it associative? Is it commutative? And then the second problem is to verify that set difference is not commutative, and it's also not associative on the power set of S. And we're requiring that S is not the empty set here, because if S is the empty set, it turns out that the operation is commutative and associative. So once you exclude the empty set S, your base set S, then you lose commutativity and associativity. All right, so press pause, take a few minutes to work on these, and when you come back, we'll work through them together. Okay, so let's take a look at part A. So part A is commutative, and the proof of that is that if you take any old A and any old B in the integers, then you see that if you do A star B, well, by definition, that's A plus B plus AB. But because we know multiplication and addition are both commutative on the integers, then I could rewrite this as B plus A plus BA, which is exactly what B star A would be. Now, how about associativity? I believe that star is associative. If you would take 3 elements, A, B, and C, in the integers, then what do you get for if you do A star B, and you star that with C? Well, that would be A plus B plus AB, then you star that with C. Now, the trick is here, you've got to, in the formula for A star B, this is going to be playing the role of A, and then C will be playing the role of B. So you just sort of substitute into that formula the big expression for A, and then C goes in place of B. And so then you'd have A plus B plus AB plus C plus then the product of those two things. So it'd be A plus B plus AB times C. And if you multiply that out and sort of gather like terms, I guess, then you would have A plus B plus C. I'm going to put all the sort of first degree terms together. And then the second degree terms, you'd have AB, and then you have AC. After you distribute that C, and you'll also have BC as a second degree term, and then you end up with ABC. And then if you do A star, B star C, that's A star, and then in parentheses you would have B plus C plus BC, but then that means to do A plus B plus C plus BC, plus then the product of those things, so it'd be A times B plus C plus BC. And then you work out what that comes out to. You get A plus B plus C. And then the second degree terms are going to be, well, I see a AB. I see AC. And you distribute the A. And then I see BC. And I also see ABC. So from these two calculations, I can see that A star B star C is equal to A star B star C. Okay, let's examine part B now. I don't believe B would be commutative because it seems like X has a different role to play than Y does in that formula. So it stands to reason that trying to switch it will change the value. So let's just see if we can find some values that make it serve as a counterexample. So star is not commutative since, let's see, it looks like probably just about anything you would pick would work, but let's try 1 star 2. Well, 1 star 2 would be 1 times 2 plus 2 times 1 equals 4, while 2 star 1 would be 2 times 1 plus 2 times 2, which will equal 6. So clearly 1 star 2 does not equal 2 star 1. And star is not associative since, well, if we did, I don't know, maybe 1 star 2 star 3, 1 star 2 we just calculated a second ago, that came out to be 4, so this is the same as 4 star 3. So that will be 4 times 3 plus 2 times 4, so that's 12 plus 8 is 20. While if we do 1 star 2 star 3, that's 1 star, okay, what's 2 star 3? Well, that's 2 times 3 plus 2 times 2, so that's 1 star 10. And that'll work out to be 1 times 10 plus 2 times 1, which is 12. And so you see that 20 and 12 are not equal. And so there you go, it's not associative. For part 2, we want to verify that set difference is not commutative and also not associative. S is not equal to the empty set. So just let little x be any singleton subset of S, okay? i.e. the singleton x, there's such a singleton subset exists in S, so then it's that would be an element of the power set of S. The power set is just the set of all subsets of S. So I have the singleton subset of the power set of S. On this one, if you try to do anything too specific, you won't get it right because we're trying to prove a general thing. It's in general not commutative. Like, I wouldn't want to pick a particular set S and then show it's not commutative for that one particular set. I'm saying I'm wanting to prove this thing is not commutative for any non-empty S. So if I start with a non-empty S, I know that it has some singleton subset. And now if I look at X minus the empty set is also an element of the power set. So I can take the set difference here. I get X, but if I do the empty set minus X, the singleton X, then I get the empty set. And then we see that these two sets are not equal, one being empty and the other one not being empty. And let's see, for the associativity thing, what can we do there? Well, maybe we can do X minus the empty set minus X again like this. And if I group it this way, this will be the empty set. I mean, X minus the empty set is X, and then I'm taking away X, and then that will result in the empty set. But if I do X minus the empty set minus X, like so, well, that would be the singleton X minus, well, the stuff that's in parentheses would just be the empty set. And now x minus the empty set is just the singleton x there. And again, we see that these two things are not equal. So that proves that in general, a non-empty set, for a non-empty set S, set difference is not associative on the power set of S. All right. So let's talk about identities with respect to binary operations. So first of all, let's start with a binary operation on a set S. So if you have this special element, we'll call it E in S, and it has the property that whenever you take E and you start with any element little s, in either order, if you do E star S or S star E, if you get back S, and that's going to be, if this element E is special in that it does that for every element little s and big S, then we call E an identity of S with respect to the binary operation star. So E is kind of like multiplying by 1, right? Like when you multiply by 1, if you do 1 times x, you get x, right? Or if you do x times 1, you get x. So E is kind of like multiplying by 1. So let's see a few examples. An identity with respect to addition on the rationals or the integers or the reals is 0. Why? Because 0 plus x equals x plus 0 equals x. And this is true for every x in the integers or the rationals or the reals. So you see 0 here is acting like E, right? In the formula up here at the top. So 0 is what we call an additive identity. Okay. Now when you think about multiplication on the rationals, the integers, or the real numbers, there's a multiplicative identity. So the identity with respect to multiplication is 1 because it satisfies 1 times x equals x times 1 equals x. And this is true for every x in the integers, rationals, or reals. 1 is the multiplicative identity. So we all know that, 0 is a very special number, and so is 1. We've been using the fact that 1 and 0 are special all our lives, right? But it's kind of interesting to now, let's think about other operations. Do we get similar things like 0 or 1? It's like, how about if we're thinking about union here on the power set? Is there some set that you can union with any other set and it just gives you back that same set? Well, a moment's thought and you'll realize, yes, the empty set plays that role. Why? Because if you do the empty set union, just whatever set, let's say A, that's the same as A union with the empty set, which is just A. And this is true for every A in the power set of S. How about intersection? Is there something that you can always intersect with a set and you get back that same set? Well, yeah. Now, if you're in the power set of S, the biggest subset of S is S itself. So you can kind of think of S as playing the role of the universe here. So in the power set of S, S is the identity element, because if you do S intersected with A, that's the same as A intersected with S, which is the same as A, and this is true for every A in the power set of S. It's because A is a subset of S, right? If A is a subset of S, when you intersect A with S, you're just getting back A. Okay. How about an identity element with respect to composition in Sn? Now remember, Sn is the set of permutations of the set 1, 2, 3, all the way up to n, right? So we had this notation that we learned about in the previous lecture, like cycle notation or 2-row notation for these sorts of permutations. So is there one of those that's special that when you compose it with any other function, you get back the same function? Well, yeah, there is a special one. Just this one called ID, which would be, if I do it in 2-row notation, it looks like this. 1, 2, 3, ... up to n. Then it just has the same thing on the bottom here. So it's the function that sends 1 to 1, 2 to 2, 3 to 3, and so on and so forth. The identity function. Another way you can define it is just to say f of x equals x. But when you compose this function with any other, ID composed with f is f composed with ID. Gives you back f, and this is true for every f in Sn. Now you don't always get an identity element. I did several examples here in a row where you have an identity element, but it's not necessarily true that you get one. For example, for subtraction, there is no identity element. So for subtraction, like if E, let's just suppose we had some hypothetical E. So if E were an identity on Z, Q, or R with respect to subtraction, then what we'd have is we'd have E minus whatever X has to equal X minus E has to equal X, right? If I take that equation right there, X minus E equals X, that would imply that E has to be 0. I can just solve that equation for E, right? So add E to both sides and subtract X from both sides, and you end up with E equal to 0. So if there is an identity, it would have to be 0. But 0 minus 1 does not equal 1, right? So if something's an identity, you have to be able to subtract anything from it and get back the same thing. So 0 minus 1 does not equal 1, it equals -1. So 0 is not an identity. So the idea is, if there were an identity, 0 would have to be such an identity, but it's not. So there is no identity. Similarly, division has no identity on the reals minus 0. We're taking away 0 here, so we don't divide by 0. So for example, we'll do the similar sort of reasoning. If such an identity, let's call it E again, were to exist, we'd have E divided by X has to equal X divided by E, which has to be equal to X. And so if I take this equation here, that would be the same as X over E has to equal X. I could divide both sides by X because I know X is not equal to 0, and consequently I would learn that E has to be equal to 1. But E equals 1 is not an identity because, for example, 1 divided by X does not equal X. In particular, I mean, I guess it's true if X is equal to 1, but that's the only X for which that works. If X is equal to, say, 2, 1 divided by 2 certainly does not equal to 2, right? 1 divided by 2 is 1/2. So, yeah. So these are a couple of examples for which there is no identity. So having an identity is kind of special. So anytime we have a set and we've got a binary operation on that set and we got an identity, that's good stuff. That tells you that there's some chance that algebra works out nicely on that set using that operation. Probably I already slipped into using the as the article adjective when I'm referring to identities. This theorem says that whenever you have an identity, there's only one identity. So you can't have like two different identities for a binary operation on a set. So the result here is if there is an identity, which there isn't necessarily, but if there is one, then it's unique. So I'd like to prove this theorem. I believe this is the first time we've proven any theorem about uniqueness in this class. So this is a good proof because it gives you a technique for arguing that something is unique. And a pretty standard argument is to suppose that you have more than one of these things and then argue that they're equal. So we'll do that here. So let's suppose that there are two identities. So suppose, let's say E1 and E2 are elements of S are identities with respect to this operation star on S. Well then, on the one hand, if we do E1 and we star that with E2, I can certainly say that that's equal to E2 on account of E1 being an identity. If I think of E1 as an identity, when I multiply it times E2, I should get back E2. And if we do E1 star E2, well, I can also say that that's E1 because E2 is an identity. Well, certainly E1 star E2 is equal to E1 star E2, so that means that E1 has to equal E2. So if I had two identities, they'd actually have to be the same thing. The conclusion is here, the identity is unique. It's kind of a cool proof, I like it. Okay, next topic, we're going to talk about inverse elements with respect to a binary operation on a set. So the setup here is we have a binary operation on a set S, and we have to suppose that this operation has an identity. So if you don't have an identity, it doesn't even make sense to talk about inverses, okay? So inverses are you only begin to consider the inverses if you know you have an identity. So, and then take an arbitrary element, little s in big S. And so we want to think about an inverse of little s here. So if there exists some other element, possibly the same as s, but if there exists some element little t in s that has the property that when you multiply t times s, or you star t and s together, in either order that you get back the identity, then we say t is the inverse of s under that operation star. And when we know that an element is an inverse of s, then we generically use this s looks like raised to the -1 notation to indicate the inverse of s with respect to star. So I just want to point out here, I want to emphasize that s inverse does not necessarily equal 1 over s necessarily. In some cases, it can mean that. Like if we're talking about multiplication, 1 over s actually is the multiplicative inverse. But if we're talking about addition, then 1 over s is not the inverse. And so we only use that notation s to the -1 sort of generically. We're talking about like some sort of generic operation, and we want to talk about inverses. And we have to be a bit more careful when we're talking about specific operations, because that notation may not make sense in specific situations. So let's talk about addition. When you're doing addition on the integers, the rational numbers, or the reals, every element has an inverse. Every element x in z, q, or r has an inverse with respect to addition. That inverse is -x. So if you do x plus -x, that's the same as -x plus x, which is 0. And remember, 0 is your additive identity. So you see, this equation that I have here is exactly the same equation we have in the definition, if you remember that our identity E is 0. Now notice, I wouldn't say the inverse of x is x to the -1 power here. So in this particular situation where we're dealing with addition, we use negative in front of the element to indicate its inverse with respect to addition. Now if we do multiplication, well, multiplication in some ways works the same way on the integers, the rationals, and the reals, but when you start thinking about inverses, things get different. Multiplicative inverses of most integers don't exist within the integers, but in the rational numbers and the reals, most of the time, except for when you're thinking about 0, you do have a multiplicative inverse. So let's see if we can spell that out. So on z, only 1 and -1 have multiplicative inverses. The multiplicative inverse of 1 is 1, and the multiplicative inverse of -1 is -1. Because if you multiply 1 times 1, you get 1, and if you multiply -1 times -1, you get back 1. Remember, 1 is the identity with respect to multiplication. On Q and R, every element except 0 has a multiplicative inverse. In fact, if x is not equal to 0, x's inverse is 1 over x. And here that notation x to the -1 exactly means 1 over that number. We see that if you multiply x times x to the -1, that's the same as x inverse times x, and then that equals 1. So this equation is satisfied for any x that's not equal to 0, so that means that any x that is not equal to 0 has a multiplicative inverse, that multiplicative inverse being 1 over that number. When we were talking about composition on the group of permutations, we know that every element has an inverse. In fact, this is just true for any bijection. Every bijection has an inverse, and the inverse is also a bijection. But in the context of Sn in particular, we saw that if you took the 2-row notation for your function, like if f was 1, 2, 3, ... up to n, and then, you got f of 1 here, f of 2 here, f of 3, f of n here, then we saw that f inverse was just swap the rows, right? So every one of those permutations has an inverse. But like I said, this is generally true. Anytime you have a bijection from A to A, the inverse is a bijection from A to A. That inverse exists, and it's also a function from A to A. So every function on the permutation group of A has an inverse. We get uniqueness of inverses as well. If you have an associative binary operation with an identity E, then in that situation we know that if S has an inverse, then it's unique. Notice that associativity is a hypothesis here. And in fact, if you drop that hypothesis of associativity, this theorem's not true. And you can come up with a counterexample of a set with a binary operation that has an identity, but things have non-unique inverses. So associativity is important here. To prove this, let's suppose little s is in big S, and it has inverses. Let's say B1 and B2. So B1 and B2 both have this property that if I multiply B1 times S, I get whatever that identity is. Or if I multiply it the other way too, if I do S star B1, I get the identity. If I do B2 star S, I get the identity. If I do S star B2, I get the identity. So knowing that B1 and B2 are inverses, I've got these equations here at my disposal. All right, so check this out. This is kind of cool. So B1, because I have an identity, I could say, well, B1 is equal to B1 star E. If I start any element with E, I just get back that same element. But this I can write as B1 star S star B2, because B2 is an inverse of S. When I star B2 with S, I get the identity. I'm just replacing E with a different form of E, right? But now I have associativity, so I can regroup like this. I can do B1 star S star B2, and probably at this point you see where things are going. B1 star S here, because B1 is also an inverse of S, is the identity. So I can just kind of cancel that off there and have E star B2, and then E star B2 is B2. So what did we just learn? We just learned that B1 and B2 are equal. So if we had these two inverses of the same element, they actually have to be the same thing. Notice we definitely had to take advantage of associativity here. If we didn't have associativity, we wouldn't have been able to make that move. Okay, so here's a really cool example. So we're making up this new binary operation on the set R minus 2. So we're taking away the element -2, which you'll come to realize why -2 is being taken away. And then this is the definition of the operation. A star B is AB plus 2A plus 2B plus 2. So I have a number of questions about this operation. Is it commutative? Is it associative? I should say, is there an identity in the set with respect to this relation? So is there some identity? And we know from past experiences there may or may not be an identity. And then part D kind of depends on, well, part D does depend on part C. If there is an identity, then that allows the possibility that you have inverses. Without an identity, you can't even talk about inverses. But if there is an identity, we want to know which elements have inverses. So let's dig in and see. So for part A here, the answer is yes. If you do A star B, that's AB plus 2A plus 2B plus 2, but that's the same as BA plus 2B plus 2A plus 2. So here I'm using the fact that multiplication and addition are commutative, and then that's exactly what B star A is. And this is true for every A and B in R minus 2, the set on which this thing is defined. So here I'm heavily using the fact, to get this equation right here in the middle, that plus and multiplication are commutative. Okay, part B. Do we have associativity? Answer there is yes as well. If you do A star B star C, well, that's AB plus 2A plus 2B plus 2 starred with C. Okay, so now this gets a little messy, I guess, but then this will be AB plus 2A plus 2B plus 2 times C plus 2 times AB plus 2A plus 2B plus 2, and then you get plus 2 times C and then plus 2. And so let's see if we can expand this out a little bit. So this will be ABC. There's going to be a 2AC, a 2BC, another 2AB. So let's just see what this works out to. Okay, so this is what you get after you simplify it all out, or sort of expand it all out and gather like terms. You get ABC plus 2AB plus 2AC plus 2BC plus 4A plus 4AB plus 4C plus 6. So then I think we're going to see that we get the same thing when we do A star and then do B star C like this. So that'll be A star BC plus 2B plus 2C plus 2. So then you multiply like this, A times BC plus 2B plus 2C plus 2. And do plus 2 times A plus 2A plus 2 times BC plus 2B plus 2C plus 2. And then plus 2. And then what does that work out to? So when you compare these two expressions term by term, you see they have exactly the same terms. So these two things are equal. Okay, so it's commutative, it's associative, that's great. How about an identity element? If you want to see if there's an identity element, what I usually do is just try to algebraically solve for it to see if there is one. If I can algebraically solve for it, then I have a candidate, and then I can verify that it is an identity. So if there exists some identity, it satisfies E star A equals A, which becomes EA plus 2E plus 2A plus 2 equals A. And so if I gather the terms that have an E on them, this will turn into E times A plus 2. Then I move the other stuff over to the other side of the equation and combine any like terms, and I end up with negative A minus 2. And so I see that if I divide both sides by A plus 2, which I can do because A does not equal negative 2, because we're in the set where we've taken out negative 2. So I can divide both sides by A plus 2 and not worry about dividing by 0, and I get E would have to be actually negative 1 here. So if there is an identity, it must be negative 1. Now let's check that negative 1 actually does satisfy the definition of an identity. Now we already know that this is a commutative operation, so I only need to check that negative 1 star A is equal to A. I don't also have to check A star negative 1 equals A, because I've already checked that, because I've already proven that the operation is commutative. So we're just going to argue that negative 1 star A equals A. So here we verify E equals negative 1 is an identity. All we have to do is go, okay, negative 1 star A, well that will be negative 1 times A plus 2 times negative 1 plus 2 times A plus 2. And what do we get? Well, I see that the negative 2 and the positive 2 cancel, and then I've got a positive 2A and a negative A, so that just ends up being A. So perfect. And this is true for every A in R minus 2. And that verifies that negative 1 is the identity. Lastly, we'll do part D here to figure out which elements have inverses. Let's just let A be an arbitrary element in R minus negative 2. We're just going to try to algebraically figure out if A has an inverse, what would it be? If A has an inverse, what is it? Well, it must satisfy A inverse star A would need to be the identity, which we just figured out is negative 1. So if I applied the definition of the operation, this would be A inverse A plus 2 times A inverse plus 2 times A plus 2 needs to equal negative 1 from this equation right here. Now let's try to solve for A inverse. It's very similar to what we did the last time. I'm going to take those first two terms and pull an A inverse out so that I'll have A plus 2 left. And I'll move everything else over to the other side of the equation, and I would get, looks like, negative 2A minus 3. And now I'm going to divide both sides by A plus 2, which I know I can do because A does not equal negative 2, so I wouldn't be dividing by 0. So A inverse would have to be negative 2A minus 3 over 2, A plus 2. Well, that's a weird looking inverse. So that's our candidate for what the inverse of A would be. And this seems like it would work for any A. We just have to verify that it actually is the identity, or the inverse. So we need to do A inverse star A, and we need to get back the identity. Well, that would be negative 2A minus 3 over 2A starred with A. And according to the way the operation works, I multiply the elements together. So I'd get negative 2A minus 3 over 2A times A, plus, then I do 2 times the first thing. Should be A plus 2 there, sorry. Then you do 2 times the second term, which is just A, and then plus 2. And hopefully this all reduces down to the identity, which we know is negative 1. So Let's see. Well, one thing I can do is factor out the A inverse term, which is here and here. If I factor that out of the first two terms, I get negative 2a minus 3 over a plus 2 times a plus 2. Then I get plus 2a plus 2. Notice that those a plus 2's cancel here, leaving me with negative 2a minus 3. Then I have a plus 2a and a plus 2, and that all boils down to just negative 1. So yes, we have found our formula for the inverse. Cool. Okay, let's do a quick skills check here. First question is, I'd like you to think about what would be an identity of the power set of S with respect to union, and then separately with respect to intersection. And then I'd like to know which, if any, elements of the power set have inverses with respect to union and intersection. And then number 3 is similar to the example that we just got through working. I'm giving you this sort of contrived binary operation on the integers, and I want you to determine if it has an identity, and if it does have an identity, I want you to figure out which elements have inverses. If it does not have an identity, you don't have to bother with the question about inverses, because the question doesn't make any sense if you don't have any inverses. If you don't have an identity. So press pause on the video and try your hand at these problems, and when you're done, unpause and we'll work them out together. Okay, welcome back. I just realized that number 1 was actually one of the problems that I already worked out, so that should have been really easy. But just repeating the answer, for union, the identity is the empty set, and for intersection, the identity is the whole set S. Now, for number 2, we haven't thought of this yet. Which elements of the power set have inverses with respect to union and separately intersection? So it makes sense to ask the question because we do have an identity element for these operations. Well, an inverse with respect to union, this would be if you took a set, some set A, it would be another set that you would union to A to get back the identity, which is the empty set. Well, if you start with A and you union something to it, you're only going to get something bigger than A. So there's no way you're going to get down to the empty set unless the set you started with was the empty set itself. So for union, only the empty set has an inverse, which is the empty set itself. And for intersection, okay, we know the identity is all of S. So if you took a set A and you intersected it with something, how would you get back the identity, which is all of S? Well, when you intersect A with another set, it only can get possibly smaller. So there's no way you can take a set that's smaller than S and intersect it with something and get back all of S. So the only set that's going to have an inverse is S itself. And its inverse, the inverse of S is S itself. If you do S intersected with S, you get the identity, which is S. But no other elements of the power set would have an inverse. Okay, so let's look at this number 3. So we've got this binary operation here, and I want to determine if it has an identity and then find it. So for identities, you're going to do something similar to what I did before. If an identity exists, it satisfies E star A equals A. Well, that's an equation that I can probably solve. So E star A equals A becomes E plus A minus 2 equals A. Notice that I can subtract A from both sides to get rid of the A, and then add 2 to both sides, and I end up with E would have to be 2 if there is an identity. And then we're going to check that it actually is. If we do 2 star A for any element A, you're going to get 2 plus A minus 2, which is A. And if you do it the other way, also A star 2, this is A plus 2 minus 2, which is also A. And this is true for every A in the set, which is the integers. So yes, E equals 2 is the identity here. Okay, so now we know we have an identity. That identity is 2. So now it makes sense to ask the question about inverses. So let's think about inverses. And we can just start with an arbitrary element and think about what would this arbitrary element's inverse have to be if there is one. So let's let A just be an arbitrary element of the integers. So if A inverse exists, which I don't know it exists yet, but if it did exist, it's got to satisfy the property of being an inverse. So we know it satisfies A inverse star A equals the identity, which we know is 2. We just figured out that the identity had to be 2 here a minute ago, right? Well, that's an equation that we can manipulate. So this is A inverse plus A minus 2 has to equal 2. So I can solve for A inverse, and A inverse would have to be 4 minus A. So now we can verify, does that actually serve as an inverse for A? So we'll check it. So if we do A inverse star A, that would be 4 minus A star A. So that, by the definition of the operation, would be 4 minus A plus A minus 2. And the A's cancel, and you're left with positive 2, which is the identity. So that's good. And we need to check it the other way too. But it checks out because actually, if you think about it, this operation is commutative. So, and this works for every A in the integers. So every element has an inverse, that inverse being 4 minus that element. So that's kind of a cool example. It makes you think a little bit more abstractly about what your identity is. I didn't know that the identity just had to be like 0, and it wasn't 1. I get it. You can have situations where the identity is something weird like 2. Kind of nifty. Okay, the next topic I want to bring up is the topic of closure of a binary operation. So we start with a binary operation on a set, and then we also have a subset T of our set S on which the binary operation is defined. Now, if the binary operation is defined on S, then clearly it's also defined on T. But the question is it not only just defined on T, but whenever you take two things out of T and you star them together, will you get back a result that's in T? If that's always the case, then that's when we say T is closed. So T is closed under the operation if whenever you star two things together from T, you get back something that's in T. So T1 star T2 will be in T for all T1 and T2 in T. So let's do a couple of quick examples to illustrate how this definition works. So let's start easy. We're going to look at addition on the integers, and then the subset of the integers I'm going to look at are the even integers. Okay, so E here is the set of even integers. And I'm also going to look at a subset D, which will be the odd integers. So I've got two subsets here that I'm going to think about. E and D. E is the evens and D is the odds. I guess I should have called it O, but I didn't want to get that confused with 0. But in any event, E is the evens. Well, we know that if you take two evens and you add them together, you get back an even, right? So E is closed with respect to addition because the sum of two even integers is even. That's something we could easily prove, but I don't think it's worth the trouble to prove it right now. Next, how about the odds there? The odds are not closed, so D is not closed, since the sum of an odd number and an odd number is actually even. So when you sum two odds, you don't get back another odd, you get back an even, so the sum didn't stay inside that set D. All right, a similar example can happen with multiplication. So let's think about multiplication on the rationals versus multiplication on the irrationals. The irrationals are R minus Q. It's not hard to verify that Q is closed with respect to multiplication because the product of two rational numbers is rational. Now this isn't very hard to prove. It's just something like A over B times C over D equals AC over BD. And that's easy to see that it's rational because the numerator and the denominator are both integers. On the other hand, R minus Q is not closed with respect to multiplication. Since, for example, square root of 2 is not rational, so it's in R minus Q. But square root of 2 multiplied times itself is equal to 2, which is rational. So we have a theorem here concerning closure of an operation. So the setup is the same as before. We have a binary operation on the set S, and then we have a subset T of S. So T will be closed under the operation if and only if we can just think of star as being a binary operation on T itself, rather than thinking of it being as a binary operation on the bigger set S. Really, when we have closure, we're really just saying that the binary operation that was defined was just on the bigger set is really a binary operation on the smaller set as well. All right, so let's prove this real quick. So first of all, the global hypothesis here is we're going to let star be a binary operation on S, with T being a subset of S. And so for the forward implication, we're just going to suppose T is closed with respect to star. Now we want to say that star is a binary operation on T. So we want to show that star is a function from T cross T to T, which means, well, it means three things, right? Any two elements of T can be starred. 2, the result of this is in T. And 3, star has the function property. Let's just say it this way, star is a function. If you think about it, all these things are clearly true. I could star any two elements of S, so I certainly can star any two elements of T, because T is a subset of S. The result of this is in T is true because that's closure. We assumed that T was closed with respect to the operation, so if I star any two things in T, I get back something in T. And then the last bit also is true just because star already was a function. So 2 is a result of closure, and 1 and 3 are due to star being a binary operation on S. So we're good to go. So going the other way, if we suppose star is a binary operation on T, then if T1 and T2 are in big T, T1 star T2 has to be an element of S, since the range of star is a subset of T, is a property of star being a binary operation on T. And so there's not much to say there, right? That's just kind of happened immediately. We know that the range of star has to be a subset of T, so that means that if I star any two things in T, the result is in T. And that's exactly what closure means. Really not much to show here. It's more just sort of like an observation. But yeah, having closure just means that you get that the thing's a binary operation on the smaller set as well. Okay, one last property that we'll talk about here of a binary operation is the idea of distribution. So to talk about distribution, you have to have two binary operations. You're going to talk about one operation distributing over the other. So let's say star and triangle here are both binary operations on the same set S. So if we say star distributes on the left with respect to delta, it just means we have a setup like this right here. Like we're going to distribute A over that triangle like that to get A star B, and then triangled with A star C like so. And you can also, because we don't necessarily know that these operations have commutativity, we don't know that we can just turn things around the other way. So we have to talk about star distributes on the right as well, possibly. So that's just where A is distributing like this from the right-hand side. So we get this equation that goes with distribution on the right. And if you get both of those, you just say star distributes with respect to star. So that usually happens if you get distribution on one side and then you've got commutative operations in play, then you'll get distribution on the right as well. So you've seen these sort of properties before. We know that multiplication distributes over addition. You know, we know that A times B plus C equals AB plus AC. And we know that if you take B plus C and you multiply on the right-hand side, because we have commutativity and all that good stuff, this is AB plus AC also. But on the other hand, addition does not distribute over multiplication. So for example, if I do something like 2 plus 3 times 4, that does not equal 2 plus 3 times 2 times 4, right? Yeah, because on the left-hand side, that works out to 14. And on the right-hand side, let's see what you got there. 6 times 8, that's 48. So yeah, 14 and 48 are not equal. We know that union distributes over intersection and intersection distributes over union because, you know, for example, A union B intersects C. This is one of those things I had you prove, like, you know, in the homework. This is A union B intersect A intersect C. And I don't need to check it on both sides because all the operations are commutative, but it's certainly true. But if I write B intersects C this way and then union A that way, well, like I said, it doesn't really need to be checked because I already know that this is equal to A union B intersects C, so there's no need to check the distribution on the right. Just distribution on the left is good enough when you're dealing, when that middle operation is commutative. All right, so then let's get rid of that. And then, yeah, we also have the similar property that A intersect B union C is equal to A intersect B union A intersect C. And both of these properties here, this is true for every A, B, and C in the power set of S. Okay, so I want to give you a little peek into abstract algebra to finish this discussion up. So abstract algebra is a class that this current class you're being prepared for. If you're thinking about algebra, you're thinking about things like, what's the general theory for things like solving equations? And so, you know, the most basic kind of equation that you might want to be able to solve in a general setting is to be able to solve a linear equation. I mean, it's just one of the most basic things that you ever want to do in algebra. I mean, when you go back to the very beginnings of your algebra training, that's probably one of the first things you did was like, learn how to solve a linear equation. Then you solve a quadratic equation after that, right? But first linear. So if you think about what goes into it, what do you need to solve a linear equation? So let's look at this on the left here. A plus x equals b, where a and b are just integers, okay? What do you need in order to solve for x? Well, the way you would solve for x here is you would subtract a on both sides, right? So you might do it, so, or add negative a to the left-hand side of both sides of this equation. So you would go, okay, well, if a plus x is equal to b, then I'd have negative a plus x, plus negative a plus x equals negative a plus b. So this equation is true because it just reflects that addition is a binary operation on the integers. So if equals are added to equals, you get equals. The function property is being employed here. So adding negative a on both sides, I'm saying this and this are equal, and I already assumed that that and that were equal, so equals are being added to equals, right? So this is the function property. But then, okay, if I want to actually cancel those a's off, I got to use associativity. So I do negative a plus a, so grip it like that, plus x equals negative a plus b. Okay, so notice that I'm going to keep track of some of the things we needed to do here. So we needed associativity. Also, one thing that we took advantage of is inverses. So the negative a was the additive inverse of a, right? So I knew that it existed, so I used it, and I used associativity here. And then to finish this thing off, you would say, well, negative a plus a is 0. And then we know 0 is an identity, an additive identity. So this comes out to give me the answer, x equals negative a plus b. So we also needed identity, the existence of an identity, okay? So really, besides having a binary operation was important too. Maybe I should just go ahead and make note of that. So we had a binary operation here. So there were kind of 4 things in play. We had a binary operation, and that binary operation, addition in this case, had associativity. All the elements had inverses, and there existed an identity. Similar things come up whenever you look at just solving like ax equals b over here. And here we'll have the a and the b be non-zero real numbers because I'm going to do some division. Yeah, I mean, you would do a similar sort of process, right? So you'd go, okay, I want to isolate x, so I'm going to multiply both sides by a inverse. So here I'm just using, again, this is just using that multiplication. When you think of it as a function, it has the function property. So I'm multiplying equals when multiplied with equals are equals. And then regroup a inverse a times x equals a inverse b. Okay, so now I'm using associativity. Going from here to here, I used associativity. And then when I multiply a inverse times a, I get the multiplicative identity, which is 1. And then the multiplicative identity when you multiply times x is just x. So you end up at x equals a inverse b. But again, it was the same property. So you had a binary op that's associative, has an identity, and all elements have inverses. A was just sort of an arbitrary element in that set, and I knew it had an inverse because it wasn't equal to 0. Remember, A inverse, when you're doing multiplication, is 1 over A. So as long as A was not 0, we had an inverse. Well, these properties, having a binary operation that's associative, you have an identity, and all the elements have inverses, it's so important that we give things with those properties a special name. It's called a group. So a group is just any old non-empty set along with a binary operation star defined on that set G that satisfies the following properties. Associativity, you got an identity element, and every element has an inverse. That's exactly what you need to solve a linear equation. So groups, when you take abstract algebra, is the primary object of study. In fact, we teach at our university 2 courses in abstract algebra 1 and abstract algebra 2. The entire first course is a study of groups and properties of groups. Groups are very powerful, and there's lots of examples of groups, and you'll do all kinds of cool stuff with them. We use this notation for groups. We put the name of the set along with the name of the operation because the operation is an essential part of it being a group, right? Because a group is a set, yeah, but it's a set and it's got this operation on it that has some special properties. So G comma star is our general notation for a group with that operation. So here are a few common examples. The integers with addition is a group. If you think about it, we know that addition is a binary operation on the integers. Check. We know that addition is associative. Check. We know that there's an additive identity. 0. Check. And we know that every element of the integers has an additive inverse. If little a is an element of the integers, its additive inverse is negative a. So there's a group. The real numbers take away 0 along with multiplication is a group. Okay, so certainly multiplication is a binary operation on this set. We know multiplication is associative. We know that there's an identity element. The identity element is 1. And we know that every non-zero real number has a multiplicative identity. If x is a non-zero real number, its multiplicative identity is 1 over x. Check, this is a group. Also, the rational numbers minus 0 forms a multiplicative group as well. This set that we saw recently, the permutation group, so this is the set of all permutations from the set 1, 2, 3 up to n to itself. So it's all those bijections from 1 through n to 1 through n. That forms a group. So we know that composition is a binary operation on that set. That was a theorem that we previously gave. We know that that operation is associative because composition in general is an associative thing. We know that there's an identity function. That's just the function that does f of x equals x. It's the dummy function, right? That you plug in x, you get back x. And we know that all those functions have inverses because they're all bijections. And we know that any bijection from a to a is invertible, and the inverse is a function is a bijection from a to a. So we know all those things have inverses. So these are just 3 examples of groups. I could take you to the land of matrices. I won't get into that because I don't know that everybody who's taking this class has had linear algebra. But if you have had linear algebra, if you, for example, would look at all of the n by n matrices whose determinants are not 0, that would form a group with respect to matrix multiplication. Or if you just took all n by n matrices, regardless of the determinant, just all n by n matrices, that forms a group with respect to matrix addition. So there's a couple of different groups in the land of matrices. Anyway, there's all kinds of really cool groups in the world. I just want to give you a few examples, just a little glimpse into what the future holds for you and how what you're learning here in this course, foundations, will serve you in that course. So let's finish up this discussion with a little skills check on closure and distribution. So the first problem here, I just want you to remember that composition is a binary operation on the set of all functions from a to a. And I want to take a subset of f of a, I of a, like script I of a, and this is just going to be the set of all one-to-one functions from a to a. I want to prove that I of a is closed with respect to composition. Second problem, the question is, does division distribute on the left with respect to addition on the set of real numbers minus 0? And then how about on the right? So I want to check left and right distribution of division over addition. Third problem, I want to check that the set of even integers actually forms a group with respect to addition. All right, so press pause on your video and take some time to think about these problems, and when you're done thinking about them, unpause and we'll work through them together. All right, welcome back. So I want to show that the set of all one-to-one function is closed with respect to composition. So to do that, we'll just take any two, let's say f and g in I of a. And what we want to show is that f composed with g is also in I of a. Well, this isn't so bad as you think. So we had a theorem, and this theorem said if f is a function from a to b and g is a function from a to b and f and g are one-to-one, then the composition, oops, I stated this wrong. This should be g is going from b to c, but f and g are both one-to-one, then we know g composed with f in that order is one-to-one. So here, in our problem, we have f is going from a to a, and g also is going from a to a, are one-to-one. So in this case, you know, the b and the c, this is the b set, right? And this is the c set. They're all a. So that previous theorem just tells us that g composed with f and f composed with g, whichever order you want to do it in this case, are one-to-one. So that tells you that I of a is closed with respect to composition. If I compose any two functions in that set, I get back another one of them. Okay, does division distribute on the left with respect to addition? I don't know. I have to think about that. Okay, so let's think about this one a little bit. I mean, I don't really know off the top of my head what the answer is, but let me just put some, like, if I have x and then I do divides by y plus z, so that's x over y plus z, assuming that y plus z is not 0. But in order to distribute it, it would need to look like this: x over y plus x over z, which I don't think that's the case, right? So this would be your x divided by y plus x divided by z if I had left distribution. But we know that that's not how fractions work, right? That's not going to happen. Since I can tell this is not going to work, the best thing to do would be to provide a counterexample to show that it's not distributive on the left. So it's not on the left. Because, for example, I could do something like 2 divided by 1 plus 3 is 2/4 equals 1/2, while 2 divided by 1 plus 2 divided by 3 is 2 plus 2/3, that'd be 5/3. And those things are certainly not equal. How about on the right? Now, when I think about on the right, sort of in the abstract, it's like, okay, that'd be something like y plus z divided by x. So that's y plus z over x. But here I know that I can do like this sort of move, right? So I think actually, as long as x is not 0, which it's not because we're assuming things are in r minus 0 here, this will work. So I think it is distributive on the left. So, I mean on the right. So yes, on the right, for every x, y, and z in the set, we have y plus z divided by x is equal to y plus z over x equals y over x plus z over x. So here we're just using familiar properties of fractions, right? And then this is y divided by x plus z divided by x. So yeah, we were able to pull off the distribution like this, right? That's pretty cool. Interesting. All right. And then The third thing here is to just check that the set of even integers forms a group with respect to addition. So first thing we want to point out is that star is a binary operation on E, the set of even integers, because we had a theorem that said if you have closure, that's the same thing as the thing as a binary operation on the set. What was that? I'm going to scroll here to find the name of that theorem. Fact 5.31 was the name. So we have a binary operation on the set of even integers. Addition is associative. It's associative on all of the integers, and so on E as well, because E is a subset of the integers. 0 is the identity, and 0 is an element of E, right? 0 is an even number. So we have the existence of, so you got to have associativity, you got to have the existence of an identity, and the last thing you need is that every element needs to have an inverse. Each n in E has inverse negative n, which is also in E, since n plus negative n equals negative n plus n equals the identity 0. So we're good on inverses as well. The inverses stay within the set E, because if n is even, then negative is even as well. So there you go. There's a simple example of a group. The set of even integers forms a group. Okay, we'll stop there, and next lecture will have to do with properties of integers and a process called mathematical induction. So I'll see you again soon. Goodbye.